good news on the newspaper page. And love and tradition of the grand design, some people say it's even harder to find. Well, then there must be some magic clue inside these gentle walls. 'Cause all I see is a tower of dreams, real love bursting out of every scene. Days go by. It's the bigger love of the family.
Hey dude, what are you up to?
I'm just trying to finish up some of this list of city problems, you know? Just a typical Saturday.
You look like you're having some trouble. Maybe I can be of some assistance.
Sure, dude, I'm having a goddamn hard time with these problems.
Language!
Sorry.
Well, I guess it's a good thing that I always carry this with me.
You mean to tell me you just carry this thing around everywhere you go?
Yeah. Is there something wrong with that?
No, it's completely normal, Andres.
Right. So basically, when solving for the modulus of elasticity, all you need to do is divide the stress S by the strain T.
Oh, that doesn't sound that bad, I guess.
It really isn't. For example, this problem right here, it asks to find the modulus of elasticity for steel and gives us a stress of 1400 newtons per meter squared and a strain of 7.
So basically, all you gotta do is just take 1400 and divide it by 7, and that gives us 200 pascals for the modulus of elasticity.
You got it, dude.
Wow, who knew that when you actually take time to learn the material, it's not too bad.
Well, actually, it can still be pretty hard. In fact, I've had some sleepless nights just trying to.
Well, I did my part of the work. Why don't you go ahead and finish this off for me, pal? You got it, bro.
But
Send it to me whenever you're done. Appreciate it.
Hello, darkness, my old friend.
Zach, you know what I've been thinking about a lot recently?
What's that?
How important sensitivity is to material engineering. I mean, it's crazy how much influence certain parts have in a project.
I know what you mean, dude. It's like no matter what type of engineer you are, you have to measure the sensitivity of certain parts to make sure that when you change a part, that the effects won't be destructive.
Like in a catapult. A catapult has many sensitivities, bro. Like the tension of rope, length of a beam, and the weight of the projectile.
And if you were to change any one of those variables even slightly, it could greatly impact the performance of the catapult.
Man, I just think that's dope.
Dang, I wish I could stay and continue talking about material sensitivity, but I've got some work to do. I need to finish.
No problem, bro. I actually need to go take a nap real quick and do some stuff.
Alright, see you, dude.
Later, bro.
Man, I have so much engineering homework. It's really starting to stress me out, bro.
You know, that's actually pretty funny. You know what we've been learning in engineering math? It's just like stress. Shear stress. It's like stress, but shear.
How do you even, like... In what way are those two things even remotely connected, other than them both having stress in the name?
Well, you see, they're actually a little more closer and related than you would actually think.
Okay, actually, what is it with everybody carrying whiteboards today? You and Andreas, like, just pulling it out of anywhere. Like, what?
Do you not carry one?
No, I use paper.
I mean...
Never mind, just explain to me how my emotional stress is somehow related to some dumb engineering concept we learned in school.
Okay, so you see, when we calculate the shear stress, right, we're multiplying the statical moment, or Q, and we're multiplying that by the specific shear moment, V. And we're going to take all that, and we have to divide it by the inertia around the neutral axis, which is I, and then we take that and multiply it by the width of the beam, B.
Okay, so how does this... I still don't see how this relates to me
All
stressing
right,
out.
I'm getting there, hold on. So, this is all equal to shear stress. Okay? Now, if we can think of QV being equal to the amount of time that someone has to work, or the amount of work someone has, W, and IB would be equal to the amount of time someone has to work on that work, then we can start to see the correlation.
Okay, I'm still not seeing it. I don't get it.
All right, okay. So if we increase the statical moment, right, or we have a decrease in the width of the beam, then that results in an increase in shear stress. Just like if we were to have an increased workload and a decreased amount of time, right? So let's say like you had to make a video and you only had one weekend to do it.
Okay.
Then I'm sure that
but like the due date for the video was during the weekday when we have no time to do the
yeah,
video?
exactly, right? So that would result in more stress.
Okay. I'm gonna go take a nap, bro. I'm done.
What? It made sense, didn't it?
No!
Hey Zach, that looks pretty cool. Mind explaining what it is?
Andreas, can't you see I'm busy? I don't have time to explain this to your dumb. Get the out of my room.
Maybe I could.
No, get out.
It sounds like there's a lot of commotion going on here.
Yeah, I'm just working on my data acquisition software.
Oh, what is that? Can you explain it to me?
Not at all, dude. I'd love to.
Dope.
So data acquisition is the process of sampling signals that measure real-world physical conditions and entering them into the software to manipulate and analyze the numbers.
So what's that graph on your computer for?
Well, actually, I don't really know. This isn't even the real program. It's just screenshots I found online.
Oh, okay.
But I would assume if it were the real program that this is a scatter plot showing the relation of the gross IMEP with the maximum cylinder pressure.
Oh, that's pretty cool, actually.
Yeah.
Yeah, well, I guess that sounds pretty cool, bro, but we should probably get going. We're gonna be late for school.
Alright, I guess we can head out.
Oh, man, I'm tired. Oh, bro, watch out, dude.
What?
Dude, this bridge smells fishy, bro. I don't like it.
We cross this bridge every morning.
Well, like, you know how in engineering math we've been learning about factors of safety?
Yeah, and?
I never cross a bridge without knowing its tensile strength.
Alright,
now.
I guess we can figure that out right now.
So to figure out the tensile strength, basically, we just need to figure out the Brinell hardness number. So to figure out the Brinell hardness number, the equation is 2p divided by pi times d, parentheses d minus square root of d squared minus d squared. And basically that the p stands for applied force, the capital D stands for foot length, and the lowercase d stands for indentation.
You and I weigh about 260 pounds each, so that's 236 kilograms of force.
And our feet are probably about 230 millimeters in length.
And we'll probably leave an indentation of 4 millimeters.
So working all that out, we're probably gonna end up getting a Brinell hardness number of 18.78. Okay, so then that must mean that the tensile strength is a total of 52.16 ksi. So that's more than stable for us to cross.
Alright, bro, we gotta get to school.
Yeah, you're right. Oh, dude, hold up! I'm getting a phone call.
Come on, bro, we need to get to school.
Dr. Chang,
We're late.
What's up? Yeah, what's going on?
Oh yes, you may have figured out that the bridge is strong enough to hold you, but what you didn't anticipate is me rigging it with C4. Yeah, I'm the smart one in the group. I should have my own show. I'm the one worthy of being the main character.
Is that Andreas?
Holy shit, I've been spotted.
Yeah, we just got done using tensile strength. It was pretty cool.
Ricardo, watch out.
Huh? Ricardo.
We're burning.
Yo, you okay?
So cold and bleeding now.